It names after John Monash, which was a Jewish engineer who became the head of the Australian troops in the First World War. And he became like a real national hero. There's so many places named after him here in Australia. Monash University located in Melbourne, which is a very nice city where there's no COVID-19 around. And I'm inside Monash, I'm located at the School of Earth, Atmosphere and Environment in the Faculty of Science. So let's start talking about science. So my PhD project ultimately aims to combine high spatial resolution from remote sensing and crop model simulations to predict yield at the field scale. People doing this stuff for decades. What I'm trying to do here is maybe do it without no ground data at all. You know, try to imagine if we could scout the globe and zoom into a specific field and then try to guess or estimate what will be the end yield of that field in the end of the season. And that thought quite guided me when I developed my methodology. So what I try to do is taking crop models. So there's many crop models, you know how it works. You're taking a lot of inputs like weather data, soil type, farm management, cultivars, and feed it into the model, and then you get a yield prediction. Some models like AppSim not only give you the yield estimation of that season, but also simulate the leaf area index, the LAI, during that growing season. And AppSim can provide very accurate results when you feed it with the right parameters. But what do you do if you don't know anything about that field? In that case, one option is to feed it with a lot of different parameters with a range of reasonable values which are the common practices for that region. This will plot a lot of possible futures, we can call it, but also a lot of possible LAI values during that season. And the way we can correlate or connect the crop model with remote sensing is using that LAI, because we know for years that we can estimate a leaf area index, LAI, from space. I chosen to use the Sentinel-2 data, but using Sentinel-2 is limited a bit when you want to work in very high resolution. So in that case, I decided to fuse Sentinel-2 data with PlanetScope images to generate a new data set of LAI in 3 meters and daily. In order to minimize the uncertainty of the model simulations, I also detected the sowing dates for each field, so I can know when that season actually started. And finally, what I'm trying to do, I'm trying to find out of all these possible futures of LAI scenarios, which ones best represent the one I got from space. And therefore, I can estimate field scale yield without knowing actually anything about that field in particular. So that's the concept. Let's start with the sowing date detection. Previous studies always estimated the sowing dates and never actually detected the actual sowing action of the seeds in the ground. Commonly they use what they call the green up, which is the emergence of the vegetation by using vegetation indices. This is an okay solution, but commonly it's quite local when you use this linear relationship between the crops and the vegetation indices. But you know, we all seen it for decades. We had enough for using thresholds of NDVI to to get some descriptions of different phenomena. So I thought we can maybe do something a bit different. And also all these attempts have been implemented their methodology at a very large scales, like state, county, regional scales. And when I went through the literature also, I saw this one author, which I won't mention his name, that explicitly said that sowing date cannot be directly detected. And for me, that was a very big motivation of trying to get this one done. So I went back and looked at sowing. And I asked myself, okay, what makes sowing detectable from space? And the answer I got was actually using the no-tilled sowing. So the no-tilled sowing have a long list of benefits. But what's interesting about this one in terms of remote sensing, this is the actual, so no-till sowing, I should mention, if you're not familiar with it, is sowing the seeds into the ground without any cultivation beforehand. So that's the actual first field scale change since the harvest. But I asked myself, okay, but what kind of remote sensing can detect sowing from space and do it in a very rapid manner? And the answer that I found was using CubeSats, such as PlanetScope constellation. So PlanetScope is operated by a company called Planet Labs. These CubeSats are tiny. They're only 10 by 10 by 30 centimeters in size. They have 4 spectral bands, blue, green, red, and near infrared, and a spatial resolution, pixel size of about 3 meters. Their temporal resolution, the revisit time, is daily, and they can do that because there's more than 120 of these nano satellites in orbit. And here's how sowing looks from space using these CubeSats. So we can see in this very short time series of images how the farmers been progressing in their sowing. But okay, see it with our eyes, this is one thing, but automate it, it's another thing. And therefore I sit down and develop the semi-automated sowing detection method, which I'm going to present briefly now. So the method is actually taking 2 images and then mosaic all these images together to have one big nice image of the same day. And then extract the field boundaries using the field polygon, as you can see here. So we have image of before harvest on the left, and after harvest or even mid-harvest here on the right. And then I used change detection. So for those of you who are not really familiar with change detection in image processing, so it works this way. So you have a time series of images, and then you go day by day by day and looking for a change until you detect one. Although it's not quite straightforward when you try to do change detection with these CubeSats, because these CubeSats are not identical. There's, as I mentioned, more than 120 of them in space from different generations. They're just different sensors. So it's hard to tell if the change you detect between 2 different images caused by atmospheric conditions, or is it caused by noise in the image, or is it caused by actual change on the surface? And in this case study, I used more than 100 PlanetScope different scenes acquired by nearly 80 different satellites. So that was quite of a challenge. And the way to overcome this limitation, I found the principal component analysis as a good solution. And I'll show you why. So when we have an RGB image, here you can see in the middle, this is recently sown field. And when I run the principal component analysis, I get 4 components. And the first component, you can see the field, it looks very, very bright. The values are very high. And so I found the first component is very sensitive to variations of the soil, while the second component is sensitive to variations of the vegetation. And the third, also mainly vegetation, and the fourth is just mainly noise, as you can see. But using this principal component analysis enables me to get a comparable measure between different images that not necessarily identical in the signal. So the way it works is just I'm taking the first component from image 1 and the first component from image 2. And then by dividing them one in another, I get this ratio image. And you can see here in red, this is a change that has been detected. And then I do some classification of the image based on the image histogram. So here you can see in this bit here, you can see the pixel generate this classification map. And after cleaning up the noise, we get something which looks like that. And a field was determined as zone if more than 25% of it have been changed. And then just using that method, you can calculate the area that's been sown on that date. And this enables to generate this sowing detection map. I've tested this method all across the Australian wheat belt. You can see here in like darkish, dark and grayish color. I tested it over 66 different fields with different types of crops: barley, wheat, canola, chickpeas, lentils, you name it. I don't remember. There was a big amount of different types. And I wanted to see if this method will work on different soil types, different climates, different crops. So first, I used data set coming from the Australian National Variety Trials, which is like a small experimental plots where they're testing different varieties and farm managements. This one, here you can see in a small image how it looks on Google Earth. And here in this tiny one, you can see how this experimental plot looked from PlanetScope image. Obviously, this is not the same plot in all these images, but this is the common practice that they use. So this is a time series of one of these experimental plots. And you can see here in this field that inside a square, you can see the actual day when this change have occurred. So this is the sowing. But when I run the algorithm, I can see there's a change of being detected, but only the one in that square has been declared as sown on that time series of images. Let's see some results. So first, this method have been, and the results have been published last year. And I was quite surprised to see how well this method performed. So the R square was 99% for both the experimental fields and also here named Birchip. This is a commercial farm, big farm, which big farm in Israeli terms. So this one is about 65,000 dunams, or 6,500 hectares in size. It's quite an average here in Australia. And they had 50 different fields, different crops, and the results have been well in both. So out of the 16 of the small plots, 100% have been detected, and 80% have been detected for the commercial farm in Birchip. And the RMSE, in terms of like the accuracy of this method, have been somewhere between just, let's say, under 2 to about 1 RMSE in days. And just to have a comparison, previous studies achieved accuracy of about 6.5 to 12 RMSE in accuracy. So much better than other methods before. This method enables to, monitor this sowing season of that farm here. And you can see what the farmer's been doing day after day after day. And therefore we can collect this data. Okay, let's move on. And then I asked myself, okay, if it works so well for the harvest, for the sowing detection, can we also detect the harvest? So in this example, you can see this is mainly pre-harvest fields. The dark brownish colors are the crops before the harvest, and the bright colors are crops after the harvest. And if I run the algorithm here, you can see the fields that have been harvested during that time. You can actually see the progress of the farmer during the harvest. Okay, moving on. So the fusion of Sentinel-2 and PlanetScope into daily LAI index. So in the recent years, quite a few papers point out that if we can get higher and more frequent LAI dataset, maybe we can improve our yield predictions. So the problem was, there's no dataset that you can actually go and download such LAI data online. So I had to sit down and just create one. So as I mentioned, I used the PlanetScope and Sentinel-2. For those of you who are not familiar with Sentinel-2, I'm sure most of you are, Sentinel-2 is actually a constellation of 2 satellites. They both operate in 13 spectral bands. They have spatial resolution of 10, 20, and 60 meters, depends on the wavelength. And the revisit time is 5 days. And this is a very useful and very common practice way to monitor crops using this satellite. So what I try to do in my method is to take and combine the advantages of the 2 sensors together. So I took the high spatial resolution, 3 meters versus 10 from PlanetScope. Also, I took the high revisit time, daily and temporal resolution of PlanetScope, and the high spectral quality of Sentinel-2. And here in this graph, we can see on the x-axis the wavelength, and on the y-axis the spectral response. And in this graph, compare the spectral response of Sentinel-2 in the dashed line, and the PlanetScope bands in the continuous line. We can see the Sentinel-2 bands are very narrow and well-defined, while the PlanetScope bands are very wide. And for example, look at the green band. There's a lot of blue signal and red signal in it. And in the red band, we have green and some blue signal in it. So you may end up with a nice image, but it's really hard to monitor crops with it. So the way this data fusion works is I'm taking surface reflectance data from PlanetScope and from Sentinel-2, and then extract the images by the field polygon, which ends up in a time series of images of Sentinel-2 and PlanetScope. But as you see, sometimes we have holes in this time series, and this is because of clouds. Although daily images, as I mentioned, this is what we would expect, but sometimes we do have clouds. So in order to close this gap, I use a linear interpolation to close the gap, and then I resample the pixel size from 10 into 3 meters, and then separating the images into their separate bands. And then the fusion is conducted at the band level. So, and then I take the blue band from the two sensors, and then green, green, blue, blue, red, red, and infrared. And then averaging at the pixel level between the images. And then at the step afterwards, combining the bands back together into one fused image. And this way we can get time series of fused images from both sensors. Next, what I'm doing is taking 13 different spectral, 13 different vegetation indices that have been indicated in the literature to be highly correlated with LAI. And then using the Sentinel-2 LAI product, extracting it by the field area, and then repeat the same process of interpolation and changing the pixel size. The next step is using a set of linear regressions to calibrate or to convert the vegetation indices into daily LAI images. So let's say a few more words about this conversion process from vegetation indices into LAI. So here in this example, we have a 2 time series of images, Sentinel-2 LAI, and one of the vegetation indices based on the fused data. And here in the yellow squares, this is, let's say this is the day that we are processing. So I'm taking a 4-day window going backwards because future images have not been acquired by the satellites. And then between each same day images, I calculate the slopes and intercepts of the images, and then take the 4-day window of the slopes, the average, sorry, of the 4-day window slopes, and the average of the 4-day window intercepts, and then multiply that with the vegetation index. And this way we get a converted image in LAI values similar to Sentinel-2, but in 3 meters. And then what the algorithm does, it moves to the next day, and then the 4 days are different a bit. So like moving average, it goes day by day, and this way we can convert the whole data set. The field measurements have been done, or this method have been tested on 12 different wheat fields located both here in Australia, but also in Israel. So I had this great opportunity to collaborate with Ofer Rosenstein and Mani, that recently finished his postdoc at Volcani Center. And together with them, we tested that method that was developed here in Australia to see if we can also monitor wheat LAI in different environments, different soil types, obviously, different cultivars. And I'll show you the results of that experiment. We had in total 57 in situ LAI measurements. And these LAI measurements have been used to validate the accuracy of that method. So let's see some results, but we're going to start first with the surface reflectance images. Here, what we can see is the images from Sentinel-2 in PlanetScope, same day. And this is how the fused image looked like. So we can see it preserve the spatial resolution of PlanetScope quite nicely, but I can also show you it preserved the spectral quality of Sentinel-2. So here we can see in these scatter plots a comparison between PlanetScope and Sentinel-2 in surface reflectance in each band, blue, green, red, and infrared. And we can see that the point clouds are quite narrow. But if we compare the same data to Sentinel-2 and the fused images, we can see that the point clouds and the R squares are much better. So the point clouds are narrower. So we know we preserved also the quality of Sentinel-2. And this way we can monitor our crops daily using different vegetation indices if we want. But also we can monitor the LAI, as you can see here in this graph. So here this graph shows one field that have been monitored during the growing season, when the blue line represent Sentinel-2 LAI, and the blue dots represent the actual days when we had Sentinel-2 images. The red line represent the fused LAI, sorry, and the red dots represent the actual days when we had PlanetScope images. The black squares represent the field measured LAI. And the scope of this method was to get the green LAI, which is the photosynthetically active part of the crop, not when they dry out. But when we examine the data, we noticed something that has been long reported in the literature, that remotely sensed LAI tend to underestimate high LAI values, higher than, let's say, 3 LAI. So what we try to do, we use the second order polynomial regression to compensate this underestimation. And we can see that the RMSE dropped from 1.17 to 0.45 in the green LAI. This compensation approach have been tested on independent data set of wheat fields here in Australia. And the results show that it can improve the estimation of the green LAI in up to 45%, which is quite promising. And obviously we can produce nice LAI maps. This is from Sentinel-2 product, and this is the fused LAI. And we can see it preserved the spatial distribution of the LAI and the patterns, but in much higher resolution. And this one also comes daily. And therefore, we can create this nice animation of monitoring the crops LAI during the season. So let's move on to the last stage, which is the yield predictions. So let's go back to the proposed methodology, because this thing is still under constructions. It's not done yet. So here what I'm doing, I'm using the PlanetScope images to detect the sowing dates, as I explained, and then fuse PlanetScope and Sentinel-2 into daily leaf area index images. The next step is to take AppSim, crop simulations, and feed it with different parameters like weather data from the nearest station, the nearest forest soil types, and then different information about the soil properties, different farm management, which are the common practices of the of that region, and the common cultivars used in that region. And this one plots a lot of different potential futures of what yield this particular field can produce. And then finally, again, I'm trying to match the observed LAI from remote sensing with the simulated LAI, which best fit with what have been observed from space. And therefore, I can estimate the yield at the field scale. This is one of the outputs of all these simulations. So each model implementation generates something like 2,000 different simulations and potential futures. And then you see in red, this is the observed remotely sensed LAI. And the way I try to match which one of these LAI graphs best represent the observed LAI from space is by taking the highest 15% values of the remotely sensed LAI. And then first, what I've done, I used the RMSE to see which one of these simulations have the lowest RMSE in compared to the observed one. But then I found out it didn't really represent well the magnitude or the impact of the timing of the peak of the LAI and the timing of that LAI. So I introduced what I called the accuracy index, which also take into account the gap of the maximum LAI between the observed and simulated, and the gap in days between the maximum of the observed and the simulated LAI, together with the RMSE. And this way, it enables me to find the best performing simulations that suits best to the observed LAI. So these are very preliminary results. We can see here in the dashed black line, this is the simulated LAI, and in red, this is the observed LAI from remote sensing, and the blue line represents the yield. And the farmer reported that yield to have 2,300 kilograms per hectare. And the method of the algorithm resulted in estimated 2,638 kilograms per hectare for that field, which is, I'll be very happy if all the fields I'm analyzing will end up in such a low error. So after see that getting the yield estimation at the field scale is possible, so I thought, you know what, maybe let's try to generate yield maps as well. And the way I'm currently doing it is I'm taking the LAI at its peak, so the maximum LAI of the growing season, and I'm taking the yield that had been estimated for that date, so the peak LAI, and then by dividing the estimated yield with the remotely sensed LAI at the maximum of that season, it gives me conversion factor, which I use to convert the LAI map into yield map. And I'll show you one example how this one looks like. So here in this example, we have the yield map been provided by the farmer. And this field has been harvested at 18th of November, 2018. And this is the estimated yield map that I got from my method. And we can see it looks quite aligned with what the combine harvester provided. The spatial resolution is better, obviously. What have been more surprisingly was the timing. So this map has been produced about 3 months before the harvest, which is quite a great achievement. So if we'll go back to that field that I talked to you about, showed you in the beginning of this presentation. So imagine if we can go back again and zoom into that field. Now we can say that this field have been sown on the 26th of April, 2018. We have monitored that field during the growing season using vegetation indices, but also its LAI. And we estimated a yield of that field and generate a yield map for that field. And we also know when it was harvested on the 18th of November, 2018. And we now know when these grains are available in the market and where, obviously. Just to sum up things. So if we'll talk about the implications of what I showed you today. So in terms of sowing detection, potentially this one can be used as an input to crop models. We can use that one also to establish sowing dates database from field to state level statistics, and also to use to detect the harvest. And as for the data fusion, we can monitor daily crops at 3 meters and potentially use this method also for any RGB-based, RGB near-based index. And it also can be extended ones, you know, if you're using CubeSats that have more bands, as PlanetScope are already launching 8 bands sensor into space, so we can get Sentinel-2 images in 8 bands in 3 meters and daily, which is quite nice. Potentially also improve the estimations of crop yields, and this is what I'm hoping to get. And lastly, in terms of the yield prediction, we can produce field scale yield predictions without ground data. We can generate yield maps at 3 meters spatial resolution, potentially, about 2 months or maybe more before the harvest, which enables us to provide agroeconomic data in different scales. I would like to obviously thank many people and organizations as Planet Labs for providing me with their images, and the National Paddock Survey of Australia and the National Variety Trials. And also Tim McNellan from Birchip for sharing his data with me, Ben and UC from Monash University. And big thanks also to Ofer, Gregory, Nati, Victor, and Mani for all their work in Israel in conducting these LAI measurements. Yeah, that's it. Thank you very much. And I hope there was someone there.
Thank you very much, Yuval. Very interesting stuff. I have questions, but I'll reserve them and give the opportunity for others who have questions. Please unmute yourself and ask. Okay, then I'll go first. Yuval, you've shown that you can predict the yield, or at least the spatial distribution of the yield pretty well 3 months before the harvest. Now, in order to choose the right model for the season, you first have to have the information for the season, right? So how would that work in real time?
Are you talking about the model inputs?
So you've shown that you run various scenarios of the model, and you choose the one that fits the observations from space best. But that's for after you've finished measuring from space the entire season. What do you do 3 months before the harvest to choose the right simulation parameters?
True. Yeah, I agree. So what I've showed you, this is only like preliminary results. Well, what we're trying to do now, or I'm trying to do now, is to see, okay, the example I showed you is for the whole season, but what will happen if, let's say, we get up to the peak of the LAI and then wait, let's say, 2 more weeks and then try to generate these estimations. It's a good question, how accurate will it be? And this is definitely the next step. I'll be happy to share the result with you once I'm going to have them. I hope I answered the question.
Yeah, okay, yeah, it's a work in progress. It's very interesting. More questions, anyone?
I have a question, Yuval. A very nice presentation. My question is about your prediction is dependent on leaf area index. The 2 months, you assume that you can predict 2 months before the end of the season. What happens if the end of the season is very dry, or if there is a deficiency of nitrogen in the soil?
Yeah, so that's true. So this method obviously have drawbacks. You can always have catastrophe, like someone, you know, sending a balloon with fire and set the field on fire. And this is why crop models cannot get something like model like AppSim, they cannot get disease, for example, or hail damage, or something can happen, just before the end of the season. And this is where the remote sensing can compensate that limitation. But obviously, if you will be able to get the effect of these things only if you wait until the end of the season. So there will be a risk that this estimation will not be accurate eventually in the end of the season. But what I'm trying to explore now is to take the 30 years of different scenarios of the common weather that we had in that particular region, and then run it and to see what will be the 30, let's say, different potential scenarios for the end of the season. But yes, obviously there is drawbacks to everything.
Mm-hmm.
More questions, anyone? Okay, then I have another question. Have you considered forcing the model with the LAI that you are measuring from space?
So forcing the model, what's commonly called as a data simulation, is an approach that has been explored by quite a lot of few people already, especially using AppSim. We have another PhD student here at our university that she explored that possibility. I haven't seen a dramatic improvement from her work, but it's in a possibility, yeah, definitely, to try to improve it this way. I chosen a different approach to get the average LAI of for a specific day during the growing season to simulate the yield. But yes, it may improve the yield estimation eventually.
More questions?
Hello. Speak about the sowing date detection and not using the common method of like green threshold or something. But in real life, sometimes after the sowing, there is a gap between the sowing and the emerging. Why did you choose to detect the sowing and not working with the common green threshold?
Because this is a very good point. And I can tell you not the first one who asked me that question. There's two answers here. The first one is when you get the sowing date and then you fit it in the model, what happened inside the model, because I also provided with the weather data, the model itself grows the plant. So so you have the emergence inside the model, and you have the green up inside the model already. Maybe it's better to detect the emergence. I don't know, but it brings me back to the second reason why I've done it, because when you do a PhD, you need to do something new to the world, and many people already done this green up thing. And I thought maybe, the yield predictions can be improved if you get the sowing date right eventually, and not the green up. Because when you detect the green up using remote sensing, it's always about this threshold. So how much, let's say about NDVI, how much NDVI considered as a green up or emergence? It depends in the spatial resolution of the sensor. It depends in the different soil types or the crop that you're using. Because sometimes you have bigger leaves than in some plants, and some you have smaller leaves. So when having the sowing, it's something very determined. So this is the day when the crops have been sown. Now I'm going to water it with some rain and let the model itself to grow the plant. That was the concept behind it. If that's the best solution, not sure, but that's what I've done.
Yeah, thank you. And Did you?
Can I comment on this? First of all, it was very interesting, a very interesting talk. But just on this point, that's true that the model will predict when you have emergence, but it's just because of a parameter that's inside the model. I mean, there's some parameter in the model that says you have emergence after a certain amount of days or degree days or whatever for the model. So you go back to the problem of parameterizing the model.
Was it like a question or a comment?
No, I mean, I don't know if you can say anything about it, but I agree with you that it's interesting to also see the sowing date, and it's information that you usually don't have, and it's something new. But I'm not sure that that can completely replace the emergence itself, because in the model you basically need both of them.
Yeah, I agree, and this is something I intend to explore, to do some sensitivity tests and to see how much improvement having the sowing dates will have. Why did you have another question?
Have you tried to see the difference between the actual emergence day and the estimated one by your model?
No, I didn't look at it. So it's already so much work to do. So I didn't want to add another factor in this complicated story. But it's definitely interesting to see how it works.
Thank you. It was a great talk.
Thanks. Any further questions, ideas, suggestions? I'm also be very happy to get any ideas or suggestions from you. I'm sure there's a lot of great ideas here in the audience, and I'll be happy to learn and to try to implement some of these.
Sorry, me again. I think you can, for the next one, we'll ask you this question. I think when you're looking on a threshold like a green up or something like this is both the crop and the weeds that are growing there. This is something that maybe your method can overcome. So I think it's maybe good.
Okay, thank you.
A combination of question and suggestion. You saw the total yield and not the quality, and one important parameter for the quality is protein, the nitrogen in the grains, and probably you can estimate the nitrogen in the leaves, and from the upstream model you can also estimate the not just the total grain yield but the nitrogen in the grains.
Yeah, so this is one of the things that I should see if it's possible, because AppSim also obviously simulate the protein and give us more information about the quality of that yield. This is a bit harder for me to compare with using this method, but maybe I can use it because I know what parameters have been what have been the output of each simulation, to see whether I can learn also about the quality of that yield. But I decided to focus on the yield as a kilogram per hectare, the dry yield, rather than the quality. But it's definitely, the quality is very important.
Can I make a suggestion, since you asked suggestions? So
definitely, this is why I'm here.
Ideas and extra work, but I think it would be right now you detect the sowing and the harvest by looking at changes between within the pictures in a time series. I think it would be very interesting to see if you can identify also when the crop switches stages, because in the model such as AppSim you have different stages, and so you have different parameters that control when you switch, I don't know, emergence and then flowering, and it depends on the model, but there's always 4 or 5 stages, and it would be very interesting if you can actually identify when these changes occurs in a crop using the same kind of approach.
Yeah, I agree. Using such I would say complicated model, there's so many different possibilities of way to take it. One example is, okay, after selecting the right simulation, now let's see if we can go backwards and say what farm managements or practice have been used by the farmer without even knowing actually what he's done there. So yeah, I agree. Thank you for this comment, and I'll take it into consideration.
Okay, last questions, anyone? Speak now or forever. No, you don't have to hold your breath. You can ask later.
Maybe I'll say a few more words, if I may, in this last opportunity. So first, once again, thank you everyone for taking the time and listening to my presentation. And I hope you find it interesting and maybe relevant to what you're doing. And I think in the end of the day, it's a platform of doing a lot of other stuff, not only detecting wheat yield in Australia, for example. So each method separately, what I presented here, can be used to other stuff as well. So if anyone here have any ideas or you want to implement it yourself, I'll be happy to guide you through and provide you with all the support and explore maybe future collaborations in trying to do this stuff in Israel and here in Australia as well. And please reach out to me if you want. I posted my email on the presentation, and also, yeah, feel free. I'll be happy to hear any comments or suggestions if you have. If you were too shy to say it now, but I'm more than looking forward to your feedback. Thank you.
Yuval, this was a great presentation. Thank you. And I think one indicator for the success is, I think, since we've started to do these Zoom seminars, it's the first time we've crossed the 40 participant line. So yeah, it's a good turnout. Before we adjourn, if anybody would like to say something else, please go ahead. I will say that I've recorded the presentation, maybe from the second slide, because I missed the first one. And we have plans to post it to our new YouTube channel for the Institute of Soil, Water, and Environmental Sciences. So this presentation might be viewed later on. If anyone has any problem with me posting it, please contact me personally. And once again, thanks, Yuval.
Thank you, everyone. תודה רבה, להתראות, ומקווה שנתראה בשמחות.
תודה רבה.
עופר, אם תוכל להישאר רגע.
אני אשאר.
ביי.